So here's a Python example, downsample. So we will downsample an audio signal. In this case is the great rock song Long Way to Go from the band called the Identities. And what we're doing is we are using a librosa to load this mp3 file into this variable x, and then we are playing using the IPython display, and we're playing just 10 seconds of the song shifted at 10 seconds from the beginning. So this is how the song sounds. So we will take a low pass filter with the impulse response given by this right here, and we will use a downsampling factor of n equals to 2. So we have here, this is our impulse response. If we take the Z transform, we will have this here. So this is the coefficients. So Z to the power minus 1, minus 2, minus 3. And then we can have the polyphase components starting at phase 0. So we have these two coefficients, and for phase 1 we have these two coefficients. So we can use this Python indexing to conveniently have this polyphase components. So from here we go to H0 and H1, and we can do the same thing. So we will have the downsampled input signal X. So we have our original signal here, and we'll just use this indexing to get the X0 and X1. So then if we remember that the multiplication in the Z domain is a convolution in the time domain, so then the filtered and downsampled output will be given by this. We can use the SciPy signal L filter. So here we are filtering X0 with H0 plus filtering X1 with H1. So let's do this. We have our impulse response here. We're defining it here. Here we are having our polyphase components for the impulse response. Here we had our X signal, and now we are having downsampled versions of the original signal, phase 0 and phase 1, and here we are filtering and adding. So observe that each of these two filters now works on a downsampled signal, but the result is identical to first filtering and then downsampling, and we can listen to the result. So we see that the sampling rate now is half of what it used to be, and we also have this filtering. So corresponding upsamplers can also be obtained with filters operating on the lower sampling rate. So we are making use of our noble identities to have filters operating on the lower sampling rate. So we have this, they are linear time invariant, and we can exchange their ordering. So we are redrawing the polyphase decomposition for an upsample, followed by a filter at the high sampling rate as follows. So here we have the delay elements shifted to the output. So we are shifting the delay elements to the output. So we have upsampling followed by a low pass filter just here. So using the noble identities, we can now shift the upsampler to the right behind the polyphase filters with changing their arguments from Z to the power of capital N to Z, and before the delay chain. So we have polyphase components given by this diagram here. So this is a picture 2. So again, this leads to a parallel processing with n filters working in parallel at the lower sampling rate. We have n filters in parallel at the lower sampling rate. So the structure on the right with the upsampler and the delay chain can be seen as a deblocking operation. So each time the upsampler let a complete block through, it is given to the delay chain. So in the next time steps, the upsampler is stopping letting through, and the block is shifted through the delay chain as a sequence of samples. So this can also be seen as a parallel to serial conversion. So with the polyphase elements y of I of z, the processing at the lower sampling rate can also be written in terms of the polyphase vectors. So observe that if we have more than one filter, we can collect the polyphase vectors into polyphase matrices.